Good morning and welcome back to Dr. Logic Awkwardly Does Logic. In this video, I've got something very interesting to tell you about System K. So you remember how in the previous video, we proved a theorem whose main connective was a possibility operator. And this is cool because we didn't have any of those in K. Now, think a couple of videos back to when we were talking about admissible versus derivable rules. And I gave you an example of a rule that is admissible in K precisely because it cannot prove anything that has a diamond as the main connective. And that is the rule, if possibly phi is a theorem, then phi is a theorem. So this is admissible in K because you will never have anything that has possibly as the main connective. So possibly phi will never be a theorem. However, we have just seen that it is possible to have possibility theorems in system T. This means that that rule, which was admissible in K, is not admissible in T. Why not? Because it would allow us to prove false things. So let me show you, because this is pretty cool. It also gives us the opportunity to see exactly how showing validity in T frames, reflexive frames, intersects with what we can prove and what we cannot. So it's a nice little example to bring together a bunch of different threads of things that we've been talking about. So we had this theorem that we proved in the previous video, namely that it's possible that P implies necessary P. Now, suppose that we had the rule that says if possibly phi is a theorem, then phi is a theorem. If we had this rule, so if this were admissible in T, then this is what we would be able to do. First, we can write down our theorem T2 because we've already proven that, and that says possibly P implies necessary P. Now, call this rule, I'm just going to give it a name, I'm going to call it star. If we had this rule, we could then apply it to line 1 to get that P implies necessary P. So this is by rule star, which isn't really a rule, and apply to line 1. Now, we can also write down the T axiom at any point, which is that necessary P implies P. But you take lines 2 and 3 together, put them together with propositional logic, and you get the biconditional between the truth of P and its necessity. But this isn't the case. So if the rule star were admissible in T, then we would be able to prove this biconditional. But what we will show using semantic methods, this can be falsified on a reflexive frame. And that means that if we had this rule, we would be able to prove something that isn't sound. So let's see, how is it that we can take necessary P if and only if P and construct a reflexive frame where it is false? So what we need to have is we need to have one of these sides true and the other side false. Now, I'm just going to start off, and so here's our first world W, it's reflexive, so I've got that arrow. And I'm just going to say, let this be the world where P is true. That makes it easy because all you have to do is assign truth to this atom. But then that means we need to have necessary P being false so that these are in fact not equivalent. In order for necessary P to be false, W has to be able to see some world, which can see itself. We'll call it W1, where P is false at that world. Now, here we're also going to have that necessary P is not true, or not necessary P is true. So just two different ways of writing the same thing. And that's because W1 can see itself and it can see that P is false. But here we have a case where P is true at world W. It can see a world where P is false, so P is not necessary. And here is how the truth and the necessity of P come apart. So if this rule were admissible in T, then we could prove something that's not sound And we see that that's not sound because we can give a reflexive frame that makes the formula false. So the rule that was admissible in K is not admissible in T. Isn't that interesting? Anyway, we've got more interesting facts to come, so join me next time. Until then, cheers, take care.